Hello, everyone, and welcome to this week's edition of Armagh Astrobytes, where we take astronomy and break it down into bite-sized chunks. We're joined again by Professor Michael Burton, who's the director of Armagh Observatory and Planetarium. So today we're going to talk about the death of stars. So last week, Michael, we learned about the life of stars like our sun. We heard the sun is a phenomenal 5 billion years old. Do all stars go on shining forever like this?
So we learned that the sun sat on what's called the main sequence, quietly burning hydrogen into helium in its core. It's been doing so for 5 billion years, and it's going to continue doing so for another 5 billion or so years. But in fact, eventually it will run out of its nuclear burning core. It will run out of hydrogen, and that's when interesting things start to happen inside its core.
Okay, so what happens when our sun eventually runs out of hydrogen?
Well, essentially what's happening inside the nuclear burning core is that the energy production from nuclear fusion is providing the pressure, basically the temperature, to support the star, the sun, from collapsing against under its own weight of gravity. If that hydrogen burning stops, then it can no longer support itself. And what happens is the core starts to collapse slightly and gets hotter. And it gets hotter enough that the next element, helium, the hydrogen's burnt the helium can now burn, and it can burn to carbon. And in doing so, it produces more energy, and that holds the star up. But in doing so, other things happen inside the star, and essentially the way radiation passes through the star, what's called the opacity, that changes. And basically, the star starts to expand and it grows in size. So the nuclear burning core is now burning helium, but this rest of the star is expanding. It becomes much, much larger. It expands to perhaps about the size of the Earth's orbit, maybe 100 times larger. In doing so, the temperature drops. It drops to maybe 3,000 degrees from the current 6,000 degrees. And that turns it red, because at 3,000 degrees, that's the color of red light. But because the star is so much larger, the luminosity goes up, and you end up with a star perhaps about 2,000 times more luminous than the sun is today.
Okay.
And we can see some of these red giant stars. If you do look up at the sky on a dark night, your eyes are sensitive to the red coloring. And those little red stars you see, here's a picture of one, are generally these red giant stars, stars which have passed their main sequence evolution and are now burning helium after carbon in their cores, and they shine up as these red giants.
And you can actually see one of these within the constellation of Taurus in the springtime.
Yes, you can indeed. Aldebaran, one of the brightest red giant stars in the sky.
So what happens next to a star within this red giant sequence?
Well, the sun cannot keep burning helium to heavier elements indefinitely. It will run out of its helium-burning helium fuel as well. And at that point, the sun will start to contract in again at its core, but it never gets hot enough to actually burn to the next phase of nuclear burning. And what then happens is that the envelope starts to drift away. The envelope expands, it's blown off, and it forms what's called a planetary nebula. That's what we're seeing here. Basically, it's the discarded gases from the star. It looks a bit like a planet, a bit like Saturn. At least that's what the first astronomers who saw these through telescopes, they saw these fuzzy objects, they saw these nebulae. But right in the very center is the burnt out core of the star. It's compressed to about the size of the Earth. It turns to a new form of matter. We call it degenerate matter, more commonly known as a white dwarf. It's about maybe 50,000 degrees, and essentially it's the burnt out cinders from the star, and it now will slowly cool for the next billions and billions of years.
Wow, and do all stars die this way?
Well, actually, no, they don't. So I've just told you about the end of a star like our sun, but in fact, stars which are more massive, stars perhaps about 8 times as more massive than the sun, actually continue to burn the elements in their core after helium. So there's basically really massive stars actually burn their fuel far, far more prodigiously. The words live fast, die young apply to the most massive stars. They can go through their evolution in literally millions of years rather than billions of years. And when they get through the helium burning phase, they can actually burn the helium to carbon, and the carbon to neon, the neon to oxygen, the oxygen to silicon, and eventually the silicon burns into iron. But iron is the most stable of all the elements, the nucleus is, and you can't get any more energy from fusing iron. And essentially at that point, the star is no longer able to produce energy to support itself. And literally it collapses in on itself under the weight of its gravity in a fraction of a second. And that collapse leads to the most almighty explosion, which actually blows the outer parts of the star apart, whereas the inner part collapses in. What we've got is what's called a supernova explosion.
Wow, and have we ever actually seen a supernova?
Well, the last bright supernova actually was about 400 years ago. It was seen in our galaxy in 1604 by Kepler, amongst many people. That's Kepler, the famous Kepler's laws of planetary motion. However, we haven't had a nearby supernova for that length of time. The most closest one to us actually took place in 1987 in our neighboring galaxy, the Large Magellanic Clouds. And here's a picture of it. It's called Supernova 1987A, or SN87A to the astronomers. And you can see a before and after picture. Basically, there was a faint star, faint because it was so far away. It's 50,000 light years away. And then one day it literally blew itself apart and a new star appeared, a naked eye star appeared in the sky where there wasn't a star before, and it remained that way for several months before it faded from view. What was actually happening, of course, was that there was a supernova and there was this expansion, that the envelope was blown off at the thousands of kilometers a second, and it started to form what's called a supernova remnant. And the picture down below is actually 7 years later, and we have here the birth of a supernova remnant.
What exactly is a supernova remnant?
So here's a picture of perhaps the most famous supernova remnant, and essentially it's the expanding debris from this almighty supernova explosion itself. So the gas has been blown off at speeds, it can be up to 10,000 kilometers a second. It's moving away from the debris of the star. And that expanding shell of gas actually sweeps up the material in interstellar space. It heats it, it lights it up, and we get this spectacular glowing nebulae, very hot gas because of the expanding blast wave. It's enriched with the elements produced inside the star by the nuclear burning core. And indeed, the compression can actually lead to the triggering of new star formation enriched by the elements from the nuclear fusion process. But left over behind in the very core, we have another state of degenerate matter, but this time it's no longer a white dwarf. The white dwarf is actually not able to hold up the star itself. It collapses further to the density of a neutron. The whole star to a density of a neutron, that makes it about 10 kilometers across. And that object is actually rapidly rotating, but I'm just going to show this again because my image has stopped. And we have in the center, we have a flashing star called a pulsar, where literally the star is rotating around itself many times a second. In the case of the famous Crab pulsar here, about 30 times a second. This image has been slowed down so you can see it. And this is the end state of the star. Sometimes, in fact, it's not even able to hold itself up as a pulsar, and it collapses in completely and forms a black hole where no light at all can escape from it. So this is the end point of the evolution of the most massive stars and how they die.
Wow, amazing. And pulsars are actually my favorite part of astronomy. I find it absolutely amazing that something so dense can be compressed into something that's about 10 or 12 kilometers across. It's absolutely insane to try to imagine that. So thank you, Michael, for taking me through that and explaining how the most massive stars end their lives. And thank you everyone for listening. Next week we'll be learning about our own galaxy, the Milky Way. So thank you, Michael.
Thank you, Courtney, and goodbye for now.
And we'll see you all next week.